In this video, we are going to discuss continuity. Continuity is a fairly straightforward topic. Intuitively, it's pretty easy to grasp what the idea of continuity is, but there are a couple things when the nitty details, the gritty details, can sometimes be a bit tricky. Our 4 learning objectives are: 1, know what continuity is; 2, be able to figure out where a function is not continuous. Those are the points of discontinuity. 3, be able to know and use continuity theorems. That's very similar to number 2 with figuring out where things don't work, where they're not continuous. And number 4, use the intermediate value theorem to prove a function has a root, also called a 0, in a given interval. So starting off, just based on intuition, take a look at the pictures and say, which graphs would you say are continuous? What's about top left? Is this continuous? Yeah. This one? No. Top right? No. Bottom left? No. Bottom center? Yes. Bottom right? No. Basically, when we're looking for continuous, we're saying no holes in the graph, no gaps, or no jumps. If you have no holes, no gaps, and no jumps, you have continuous. A very quick, easy way to have the graph understanding: can you put your pencil down and draw the entire thing without ever picking your pencil up? Looking at the top left, I could start over here, and I drew the whole thing without having to pick it up. But on this one, I can say there's no point, but then I have to jump up and continue. Even going down to the bottom left where it looks like, oh, hey, check this out, I can do this and trace out like a circle and keep going. Well, that's not really what's going on. When we're drawing this, remember that the open circle means this is not a part of it. So to get past it, I would have to skip and keep going. That's why it's not continuous. I have to pick up my pencil to go over the hole in the graph and then continue onward. Continuous, no holes, no gaps, no jumps. Very quick, intuitive way to describe them. But here is the more precise version behind it. A function is continuous at a number a if the limit of the function at the number a is actually equal to the function value at a. That's the formal definition of continuous. Now, of course, this piece is true when 3 conditions are met, because this statement implies kind of surreptitiously 3 things. Number 1, the function is actually defined at a. If the function doesn't make sense, how could it be continuous at a place that doesn't make sense? This is the piece that is talking about having something like no holes. Back in this problem on the bottom right, the function is, or I'm sorry, bottom left. The open circle here, and I should switch the colors to make it easier to see. The open circle says there's no function there at all. So how could the limit equal the function value when there is no function value? It can't. The second one, the limit has to exist. Going back to the last screen, how could we possibly have continuity when the right-hand limit and the left-hand limit don't match? If the limit does not exist, that's saying we would have a jump. We can't have any jumps. And the last one is the actual equation part. The limit does equal the function value. that would be the bottom right. This is one where the limit exists, left and right are both coming the same, and the function is defined, but the function value still have to hop upward. You still have to jump upward to get it. That's creating a gap in the graph. No holes, no gaps, no jumps. If we can avoid those, we have continuous. The function value must equal the limit value. So, if it's not continuous, instead of saying not continuous all the time, the terminology that is used is actually discontinuous. It's discontinuous at the a value of 4. Another word that gets used is discontinuity. F has a discontinuity at the a value of 4 or the x value of 4. Just knowing when we encounter the terms discontinuous or discontinuity, we just know it means not continuous. So take a look at this graph. For which x values is this graph discontinuous? Not where is it continuous? Where do we have the problems? Okay, coming straight down, that's an x value of -7, so it's discontinuous with the hole in the graph at -7. And we have a hole in the graph, or perhaps we should say a jump in the graph because it is defined, but we still have the problem at x equals -2, and this jump over at x equals 3. Those are the points where the function is discontinuous. We could say the graph of f, or our function f, is discontinuous at x equals -7, -2, and +3. Well, what about equations? We had a cool little graph, but what about the equation? If you'd like, we could type this into the calculator and say, hooray, we'll type it in. This one would be tricky even there. If we factored the numerator, you notice that this has the form x minus 1 quantity squared, and then we'd have over x minus 1. Yeah, so it simplifies, and we wind up saying x minus 1, which would give us a graph that looks like, pretty much like this. Where is this graph discontinuous? Well, the one that I have drawn here, that's y equals x minus 1. This is not the same thing as that. Remember that conversation we had when we were discussing like asymptotes? Because we cannot plug in x equals 1 to the denominator, this is a piece where we would actually have a hole in the graph. A graphing calculator will not show it to you because it's not going to put the big circle there. You would be able to find it in a table of values, but this is one that's easier just to recognize. We have a hole in the graph. So where is our function discontinuous? At the x value of 1. We have a hole in the graph. Continuing onward, where is this function discontinuous? Okay, well, what does the graph look like? Do you remember what 1 over x looks like? It has, our parent function looks kind of like this. And so if x is not equal to 0, we have all of this, and we know that this part isn't even defined for 0. But because of the piecewise, we would have x equals 1, or I'm sorry, y value is 1 when x is equal to 0. So the function is defined everywhere. The domain is all the real numbers. But where do we have a point of discontinuity? Once again, at x equals 0, because of the enormous gap between the defined value and others. Number 4, where is this discontinuous? We have another piecewise defined function, but I want to point something out to you. Is this piece looking familiar? Yeah, we just did that one right here. And so what I'm going to do is, because I don't want to take a bunch of extra time, I'm going to say haha, and I'm going to copy it. Voila. This is the graph for the top. Actually, I want to match the colors. Now, if x equals 1, the height has to be 0. So we'll plug that in. Now, where is the function discontinuous? It's discontinuous nowhere. The problem that we had before was that the graph had a hole at x equals 1. And if we had 1 minus 1 plugged into the red, that would give us 0. So we know the red graph, which is the top half of our piecewise function, was limiting on 0. That was telling us limit of f of x as x was approaching 1 was a height of 0. Well, now our function value actually is 0. So we have the limit equal the function value at x equals 1. Basically, the hole that was there, we just filled it in. So it's continuous everywhere, discontinuous nowhere. What about the greatest integer function? Where is it discontinuous? Remember what the graph looks like? The graph of the greatest integer, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Our catalog of essential functions, it's like, we have to know lots and lots and lots of functions. This one had the image from 0 over. Yeah, it was a step function where we had there and over. Man, I can't seem to get this stuff drawn correctly. The greatest integer above 0 is 0, so we would have an open circle, closed, open to closed, open to closed. So where do we have points of discontinuity when we continue the pattern? Not everywhere. We don't want to say everywhere, because here is 1/2. Do we have a point of discontinuity at a half? No, because the limit and the function value are going to be the same. What if we were at like 0.00001? Well, we could still get closer to 0 on the sides. The point where we have problems, or the points where we have problems, are everywhere that it's jumping. Where is it jumping? Now, Jessica, you said whole numbers. Whole numbers refer to like 0, 1, 2, 3, 4, 5, 6, but they do not include negatives. We still have problems with negatives. It's all of the integers. -1, -2, -3, ... 0, 1, 2, 3, ... Any integer is where a jump is going to occur. Those are the points of discontinuity. Okay, the same way that we were able to define a one-sided limit, we can further discuss one-sided continuity. Basically, if it's the limit, if a one-sided limit actually equals the function value, then it's a one-sided continuous. What type of a function would need one-sided continuity? Well, the first one that comes to my mind, how about the square root of x? It doesn't exist for the negatives. So if we wanted to talk about continuity at 0, we couldn't have continuity at 0 because the left-hand limit does not exist. But we can have one-sided or right-hand continuity at x equals 0 for the square root function. So based on this example, where would we get continuity? Where would we get one-sided continuity? What does this graph look like? Just shifted 2 to the right. So where do we have one-sided continuity? Right-handed continuous at x equals 2. And it would be continuous at each of the other points along the rest. Not defined for anything to the left of 2. Okay, what about this one? The greatest integer. Where do we have one-sided discontinuous? And I'm going to back up and once again erase some of this extra scratch piece that was not on the video but came up based on a student question. And oh, didn't want that. Take this and we can copy it. Oh man. Escape. Copy, back, down, 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 paste. Voila. Where do we have one-sided discontinuities? One of the important characteristics I did not mention of the last problem, at x equals 0, the function is defined. So the limit closing in from the right will equal the definition or the function value. We had the right-hand limit as x is approaching 2 actually did equal the function value. This is one-sided continuity. Well, here we have the function value. And so we would have a right-hand limit closing in on the function value. Where we had this piece with the integers, where we said it was discontinuous, at all the integers, we do have right side continuity. What about left side continuity? We don't have it. Doesn't have. Man, I'm crowded. Why not? Well, when we are looking at the left-hand side, closing in, it's approaching the limit. The left-hand limit here is 2, but the function value is 3. The left-hand limit does not equal the function value, so it is left side discontinuous. The right-hand limit does equal the function value, so it is right side continuous. Okay? We're seeing the limit value must match the function value. Looking at this last one, or here, notice, or do you recall, I was saying it's continuous at all these points? rather than trying to draw a whole bunch of dots, we could say it's continuous, or right side continuous at 2, and all the way up. If we say something is continuous over an interval, or right side continuous, left side continuous, if we say it's continuous over an interval, we're saying it's continuous at every single point inside the interval, which is what this definition is telling us. So, show that this function is continuous on -2 to 2 with the points being included. Well, that's just saying we need to have it with the limit approaching some number a has to actually equal the function value whenever we have -2 and this number is in between. This is what we need. To say that they're continuous, they have to have this part be true. One piece that's kind of nice, let's take the limit as x approaches a of x squared minus 4. Well, we could do direct substitution and say that's a squared minus 4. As long as it makes sense, as long as it's defined. Does this a value, or is the function defined for the a values we picked? Yeah, because our domain would have been, this stuff has to be positive. So we'd say plus 4, x squared is greater than or equal to 4 will work for the domain. Take the square root, and we would have 2, or x has to be greater than or equal to 2, or x has to be less than or equal to -2. This is our domain. Do you see the problem? The domain of our function is everything from -infinity up to a -2. Then it's not defined when we're taking square roots of negatives, but then it picks up again from 2 to infinity. Could we possibly have this be true? Okay, you're shaking your head no, and you're absolutely right. How could we have the limit equal the function value when this function value does not exist? It can't. The problem that we were asked to do here is impossible. Now, if we wanted to say, show that it is discontinuous on the interval, then we've nailed it, because the function value does not exist. But what about the actual endpoints of 2 versus -2? Wouldn't the function be continuous at -2? Well, if we're looking at a graph that's like this, how could it be continuous here at -2? There's no right-hand side to close in on. It would be left-handed continuous. Or here, how could it be continuous at 2? There's no left-hand side. But we would have right side continuous, but we weren't asked for one-sided discontinuous because it's not the total limit. This is enough to demonstrate that it does not work. We would have a discontinuous function on this interval. If we were asked for continuity, we would just have to go through some algebra and show that the limit equals the function value, but please verify the function value actually makes sense. Please verify that, where is it? Back. Verify the function value exists. Verify the limit exists, and verify that they actually match up. It's easy just to go through and say, hey, I'm going to do a bunch of cool work here and say they match up. But if it doesn't exist, then your algebra was based on false assumptions and you've got crap work anyhow. Make sure that the pieces actually are met. And I got to keep going, keep going. Continuous on an interval. Okay. Suppose we actually have a piece where we want to add functions now. So we have a picture where the graph of f is continuous. The graph of b is continuous. I'm sorry, the graph of g is continuous. We can add continuous functions together and it will still be continuous. We can subtract, we can multiply, we can divide, as long as dividing makes sense. We can multiply by constants. All of those things will still work. All of them are based on our limit values. Why does this first one have to be true? We are saying f of x plus g of x is continuous when f is continuous and g is continuous. Why does this have to be true? Well, think in terms of our limits. This tells us the limit as x is approaching a equals the function value. And similarly, the limit as x is approaching a of g of x is equal to g of a. That's what the definition of continuous tells us. Remember, this piece is saying the limit as x approaches a of f plus g of x. We need this to equal f plus g of a. But based just from algebra 2, we already know this part's going to be true. Going back to algebra 2, we know that you can decompose functions with addition by splitting them up. Going back to our limit pieces, we had a limit law that said if we have a sum, we can split this up into two limits. And so we get precisely what we need. Using the limit laws from our previous work, that would have been section 1.6, we can split up the limits and have this part. Using algebra 2, we can split up the function and have that part. But those two things together are telling us exactly what we had over here. I did not write up the formal proof. I did not write up the details of a beautiful proof. All I did here was show you kind of the elements of it, the logic behind it. But there's a quick verbal scratch work explanation of why the theorem is going to be true. We had the same type of limit laws for division, for multiplication, for subtraction, and for constants. It's the same idea. We're just using a different limit law to explain why each one of these pieces will be true. Some things worth noting. Polynomials are continuous everywhere. Think of a polynomial. When you draw them, do you ever have holes, gaps, or jumps in polynomials? Nope. So they're continuous for the entire real number. Rational functions are continuous everywhere, except when you run into places where they're not defined. The vertical asymptotes, the holes in the function. Thinking back to when we had this x squared minus 2x plus 1 over x minus 1, where was the only place we ran into a problem? When x was equal to 1, when the function was not defined. If we had a vertical asymptote, it's not defined at the function. If we have a hole, it's not defined at the function. Rational functions, along with root functions and trig functions, are defined everywhere, or rather they're continuous everywhere as long as the function makes sense. As long as it's in the domain, we're okay. really beneficial to remember this. Polynomials, rational functions, root functions, trig functions, they are continuous everywhere that they make sense. They're continuous everywhere as long as it's in the domain of the function. So of course, figuring out domain is an important part of working with these pieces, because if you can find where it's outside the domain, then you found out where it's not continuous. For example, here, where is this continuous? Everywhere on all of the real line, all real numbers. Why? It's a polynomial. And the domain of polynomials is the entire real line. The question was just asked if quadratic functions are, I'm thinking of trying to remember how it was phrased. Are quadratic functions not continuous everywhere? Quadratic functions are polynomials. The domain is the entire real line, so yes, they're continuous everywhere. The problem with them is that the range is not the entire real line. And so we don't have anything going on with range though, so we're still okay. Number 10, where is this function continuous? Well, you notice how we have a root function, and we have a sum with a rational function. Based on the theorems we were looking at, this will be continuous everywhere that the individual functions are defined. So if we can figure out the domain for the right piece and the domain for the left function, we can restrict and combine, do the intersection of the two domains, and say whatever they've got in common we're okay with. So what is the domain for the root function? Everything from 0 to infinity. And on the right hand side, what is the domain? Everything that's not equal to a 1. So where do we get both conditions are met? When we have everything from 0 to infinity except 1. Well, we could say the domain is 0 up to 1, unioned with 1 to infinity. Because our function has this domain, and it's a sum, product, quotient, difference of rational and root functions, it's continuous over the entire domain. This part down in the blue with our domain is the answer. We're done. What about this one? Well, it is a rational, or it is an algebraic function. It is a quotient of trig functions, where we have a trig function being added to a constant. This is the same situation. Wherever we have, if we're trying to find the points of continuity, wherever, I'm trying to think of a better way of phrasing this. If we're looking for where it's continuous, that will be the same as the domain, because it's the same type of, it fits in with the theorems we were just looking. This one does not ask us, though, where it's continuous or where it's discontinuous. It just says evaluate. Well, if the limit equals the function value, it would be continuous. So let's ask this. Is this continuous at pi? If it's continuous at pi, then we could just do the function. Asking if it's continuous at pi is the same thing as asking, is pi in the domain? If pi is in the domain, our theorems are going to tell us it will be continuous. The definition then tells us all we have to do is plug in pi and get our answer. Well, we can figure out if pi is in the domain just by plugging it in and seeing if we get an answer. If we get something that makes sense, pi is in the domain. If it doesn't make sense, we're done. So let's just plug in pi. What is sine of pi over 1 plus cosine of pi? Let's go back to our unit circle. Whoa, that shifted on me. We know pi radians is right here. What is the cosine there? What is the sine there? Remember, cosine is the distance to the left, and sine is the height. So what's the sine of pi? 0. What is the cosine of pi? -1. So we wind up with 0 over 0. Does it make sense? No. This does not make sense, which tells us, because it doesn't make sense, pi is not in the domain. Because pi is not in the domain, it tells us it's not continuous. And because it's not continuous, it tells us this limit does not exist. Or at least trying to evaluate. We're done. With further techniques, we could investigate this more, but with our current techniques, we're saying it doesn't exist because 0 over 0, we can't make any sense out of it. This theorem, take a moment and read it. Kind of looks a bit goofy. Basically, it's saying continuity will work if you're taking compositions of functions, as long as you're careful about making sure the composition is making sense. Consider this. Is f composed with g continuous at x equals 2? Keeping in mind that the graph we have here is not the composition function, so we can't just look and say, oh, here there's a hole at 2. Well, keep this in mind. F of g of 2. Does g of 2 make sense? Okay, what is g of 2? Well, at x equals 2, 2, 3, 4, we get a y height of 5, so we're saying f of 5. Does f of 5 make sense? 0, 1, 2, 3, 4, 5, we'd come up. There's f of 5. Is the limit making sense coming in? Does the limit make sense for the g of 2? Yes. The limit makes sense. The limit actually does equal the function value. And then when we switched over to f of 5, does the limit exist? Does the limit equal the function value? That tells us g is continuous at 2, which then shifts us over to f of 5, and f is continuous at 5. Because the chain of pieces is continuous at every single step, the entire function will be continuous at x equals 2. If we were to go through and actually create the graph of f composed with g, it will be continuous at 2, even though we don't know what it looks like. We know it's got to be continuous. I'll switch colors to yellow here and say, what about x equals 0? Well, that's saying f of g of 0. What is g of 0? Okay, g of 0 is 2. Is it continuous? Is g continuous at 0? So right now we don't have a problem. But what is g of 0? We said that was 2. And if we go over to, it's 3. Here's 0, 1, 2. Yep, thank you, it is 3. I was looking crooked. Thank you for catching that. So we're saying f of 3 If we come over to f of 3, 0, 1, 2, does that make sense? Does the limit exist? Does it equal the function value? So yes, this would actually check out because the chain is continuous along the chain, the whole piece will be continuous at x equals 0 as well. Similar, same graph, but you'll note I flipped the function around. Instead of f composed with g, let's look at g composed with f. So we have g of f of negative 2. Does f of negative 2 make sense? Why not? Yeah, negative 2 is here, and f of negative 2 does not exist. It's not defined. So how could we do a composition? We can't. We can't. And because the composition cannot be done, that tells us if we tried to create the composed function, the picture for it, without even knowing what the picture looks like, we know it will not be continuous at x equals negative 2. Because the limits don't work. What about at x equals 2? So we're saying g of f of 2. Does f of 2 make sense? Okay, f of 2 is, what, negative 2? Does g of negative 2 make sense? Yeah. That would be right here. So yes, that checks out. So yes, the function will be continuous at x equals 2, even though we don't know what it looks like. We would need the entire chain to stick together, the entire chain to work. I'm thinking that with this example, this stuff makes more sense now. Well, please note this piece. It's actually saying f of the limit value. It's not saying the actual function value. It's saying the limit value. So it would have been possible if we had something like a hole or a gap. Remember when we had the hole in our first example, how we had the hole at x equals negative 1 or at x equals 1? Because the limit value existed, we would still be able to have a continuous function because the limit existed. If the limit exists for the first one, you'll be okay. And if the actual function value exists for the first one, you'll be okay. That's what these two theorems are telling us. The limits need to work, and when we did the 2, or I'm sorry, this one, where we ran into problems with f of 2 not even being defined, it was so far away that there was no limit there either. With no limit and no function value defined, we're screwed. It just won't be continuous. So, let's consider this one. Where is this function continuous? Do you see the composition of functions? This is saying take cosine of x and then square it. So we would have something like g of x be cosine of x, and h of x is the function x squared, but then f is the composition of g being plugged into h. So if we want to know where f is continuous, we will need to follow through and ask where is the pieces continuous. Where is the function g continuous? Where is cosine continuous? Everywhere. So it means we are going to be plugging in everywhere into the other function. Chaining that together. Where is h continuous? Everywhere. So if we have continuous everywhere plugged into continuous everywhere, what's the result going to be? It's continuous everywhere, and we're done. Similar in structure. Let's start by keeping track of how things got moved. Let's figure out our composition of functions. And looking back and saying, wow, those composition of functions things actually played a role, right? So we'll create the just the chart mapping out our or a flow chart of operations. What's the first thing being done to x? X is being squared. Then what? Then we're taking plus 4. Then what? Then we have the root. Then what? Subtract 7, so we'd take x minus 7, which would give us x squared plus 4 minus, I want that to be clearly on the outside, minus 7. Then what? We'd have the reciprocal 1 over, which gives us, and I'm out of room, but I'm just going to write our f of x. So this is what we're looking at. We have, here can be our h, and I want to back these up because there's so many of them. I'm going to call this function A. This is function B, function C, function D, function E. That's telling us f of x is equal to the total composition E composed with D, composed with C, composed with B, composed with A of x. So, now we know from our previous theorems that since this is an algebraic function, it's comprised completely and totally of rational functions, root functions, polynomials, trig functions. Because it has that type, our previous theorems tell us this function will be continuous everywhere that's in its domain. So the main feature that we have to figure out then is what is the domain of the function. Now we can use this flowchart to figure out exactly what the domain is by keeping track of what goes into function A, what comes out of it. What goes in the function B, what comes out of it, and tracking all the way down through the end. What I would like to do, though, is actually take this same piece and go to our next page. Oh, sorry, needed to insert a new page, and simply say, what is the domain for this function? If we can figure out the domain of the function, then we are completely set. So remember, if you're searching for domain, it's easier to find the restrictions on the domain. If we're searching for restrictions, what are the things that don't work? Well, they don't work if we have to divide by 0. And they don't work if you have to take the square root of a negative number. We also know that there would have restrictions if we had to take the logarithm of a non-positive, but since this problem has no logarithms, we don't have to worry about that. These are the two things that we have to search for. If we take the square root of a negative, it's outside the domain, not continuous when the function doesn't exist. Or if we have to divide by 0, that would create either a jump or a whole gap, something, but we can't divide by 0, so that's what we've got to search for. Well, let's start off with the negative. Do we have problems taking the square root, specifically with the square root? Is this something that's ever less than 0? Well, just subtracting 4, x squared is less than 4. But when you take x squared, subtracting 4, we'd have negative 4. Keep in mind, here's our graph of x squared. Here would be y equals negative 4. Where is the graph of our parabola lower than the horizontal line? It's not. X squared, if you take any positive, it's going to be If you square a positive, it's a positive. You square a negative, it's a positive. You square 0, it's 0, which is still greater than -4. So this piece, we run into no problems. This is a piece, this inequality is never true, which means we run into no restrictions based on it. Well, the only potential problem we would have then is the square root, is the denominator equaling 0. So when do we encounter a situation when the denominator is 0? Well, adding 7 to both sides would give us this. Squaring both sides gives us x squared plus 4 equals 49. Subtracting 4 gives us x squared is 45. And then taking the square root gives us the positive or negative square root of 45. Square root of 45, I'm going to simplify, by the way. Switching colors, 45 is 9 times 5. So the square root of 45 equals the square root of 9 times the square root of 5, which is just the square root of 5. Telling me here are the restrictions on the domain. These are the points at which it's discontinuous. This is what does not work. Our domain is all the x values that are in the real numbers such that they're not positive or negative 3 times the root of 5. Since this is the domain, this is also where it is continuous. But we would like to be able to have the intervals. Well, to set up the intervals, we'll start at -infinity and come up to the smaller of them, negative. Oh, I started writing it wrong. -infinity up to -3 times the root of 5, unioned with, I'm going to run out of room here, so I'm going to erase this scratch work just to give me more room to write. I'm running out. I'll grab this stuff, bring this over, bring that over, unioned with, from 3, -3 to the root of 5, up to +3 to the root of 5, unioned with 3 to the root of 5, upward to positive infinity. This chain, this union of intervals, are all the places that the function exists based on its domain. Therefore, based on our theorems, we know this is where the this is where it's continuous, because the function is continuous at these on these intervals because the domain exists. The function exists on these intervals. That's what our last theorems were telling us. Finally, the last thing that we have to have today, the intermediate value theorem. Suppose that a function is continuous on the closed interval from a to b, and let n be some number between f of a and f of b, but f of a is not equal to f of b. Then there will exist some number c in the interval from a to b such that f of c equals n. And you stop and say, what? It's actually a lot easier to understand. Suppose we have a function, and I'm drawing this just so that it looks like this, but you can draw any continuous function. You draw any continuous function you want, and we are going to start and say we are examining the closed interval from A to B. You will note this function is continuous on the entire interval over from A to B. Yes, it's continuous in other places, but specifically it's continuous along this entire x-axis, this entire portion of the x-axis. we are also observing this height is f of a, this height is f of b. We are concerned with the values along the y-axis that are in between f of a and f of b. What the intermediate value theorem says is take any number you want along the y-axis that's in between f of a and b. Pick any height in between them, such as this height. That height is my number n. The intermediate value theorem says if I come over, I'm going to be able to hit the graph, which would drop me straight down to a number c. And that number c is going to tell me if I plug it into the function, I will get out the height. But also, that number c has to be in between a and b. Where this gets to be very beneficial is it's just a way of guaranteeing if we have a continuous function and then we have y values that are at two different y value heights. If you pick a number in between the two y values, you are guaranteed there will be an x value that's going to give it to you, that will give you the y value you want, and more specifically, the y value has to fit within a particular range on the x-axis. Where this gets to be very, very beneficial is with roots. Specifically, if we were to drag this part up and say, here is my x-axis, here is my y-axis. If I have a continuous function that crosses the x-axis, so here's my a value, and here's my b value. So your note, we're fitting the theorem. It's continuous from a to b. And then we would have our heights, f of a and f of b. Pick any height you want that's in between these. There has to be some number in between a and b that will give you the height you want, no matter what. That's the intermediate value theorem. Specifically, I want to know where is the height, where is the function value equal to 0. That's just asking where does the function cross the x-axis. Wait, I want to rewrite that. Where does f of x cross? My board's not writing right now. Okay, my board seems to have locked up a little bit. And my board froze for a moment. I think this has repaired it now. Come on. And my computer's just locking up. I don't understand what's wrong with this. Okay. The intermediate value theorem will not tell you where it crosses. The intermediate value theorem will not help you get the answer. The only thing the intermediate value theorem does is guarantee there is an answer, which we can graphically see here at C. That's it. It guarantees an answer must exist. The graph must cross the x-axis because of the intermediate value. So, how does this actually get used? What's the most common way? It's like this. Show that there is a root, or show that there is a zero of the graph for this function, 4x cubed minus 6x squared plus 3x minus 2, that's between 1 and 2. Please note, we are not being asked to find what the root is. We are not being asked to find a number. We're being asked to explain and prove why an answer must exist. So, what we would have to start by noting is f of x is a polynomial, and we know that polynomials are continuous everywhere. So, if it's continuous everywhere, we know specifically that it's continuous on the closed interval from 1 to 2. Please note this piece in the blue is starting off by saying I'm meeting the conditions of the intermediate value theorem. We have a continuous function on a closed interval from 1 to 2. The next part of the intermediate value theorem is n is a number between f of a and f of b. So we need to figure out, note that f of a, and a in this case is 1, is 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2. Crunch the numbers. 4 minus 6 is negative 2, plus 3 is positive 1, minus 2 equals negative 1. Emphasis on negative. And we have the first part there that I wrote is f of a, f of 1. Now we need f of b, which is f of 2. So 4 times 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2. Okay, 2 cubed is 8. So 4 times 8 is 32. 2 squared is 4. 6 times 4 equals 24. So we have 32 minus 24, which equals 8. 8 plus 6 is 14. 14 minus 2 equals 12. So specifically, we get positive 12. This is beneficial for us because we can see, I'm trying to think of a nice way of writing a transition. I was going to use note that, but we just used the word note that, so I'm thinking of something else. So we'll say we can see, or we can take n equals 0 and see negative 1 is less than 0, which is less than 12. That is, f of a is less than n, which is less than f of b. All that piece in the red is writing it up to say we have a number, 0, that's between f of 1 and f of 2. We've also noted 1 is not, f of 1, which was negative 1, is not equal to positive 12. All of that sets it up so that we can now conclude this piece. Writing it up, the intermediate value theorem guarantees there exists some number C that's in between, or some number C. Come on, erase. Such that such that 1 is less than C is less than 2. That's telling us C is in the closed interval at the beginning, and f of C equals the height of 0. That's the n number. But f of C equals 0 means C is a root of the function f. This whole paragraph is using the intermediate value theorem. It does not give us an answer. All it does is guarantee the existence of an answer in a particular location. It guarantees the answer will be there somewhere between 1 and 2. We don't know what, but we know the general location for it. So backtracking all the way to the beginning, remember the learning objectives that we had. With regard to continuity, you should know what continuity means. No holes, no gaps, no jumps. You should be able to determine the points of discontinuity for a function. A function will be discontinuous if the limit does not approach the function value. If the function value doesn't exist, you obviously can't have the limit approach something that doesn't exist. If the limit doesn't exist, it can't approach a function value if the limit just goes off plus, minus, or has some sort of a gap. You should be able to use the continuity theorems to be able to figure out where a function will be continuous, where a function would be discontinuous. A lot of that is tied to the domain. And finally, you should be able to use the intermediate value theorem to prove, to explain that a function will have a root over a given closed interval. If you can do those 4 things, then you've met all the objectives that we have for our studies into continuity.